So, hello everybody, welcome to the third Greenering webinar, When Industry Meets Academia, devoted to the green production of ammonia. Thank you for attending the webinar, and I am very confused because I made a confusion between CET and CEST time. So thank you for being here. And thank you also to the two speakers. So welcome to Mrs. Godbjørg Rist, who is the CEO of the company Ammonia, and Mr. Surya Josuila, who is Senior Director of the Technology Strategy Unit at Fujitsu Research of America. I propose to let Mrs. Rist and Mr. Josuila to do their talks, and then we will finish with questions. In case you have some questions, and I invite you to use the chat. So let's begin with Mrs. Rist from Ammonia.
Yes, hi. So the share screen is working now? Yeah, okay, good. So hi everyone, I'm Godbjørg from Ammonia. I'm a production engineer, and I joined Ammonia in 2018. Having not worked with ammonia or in this, any kind of research up to that point, but more in the industry. But Ammonia was founded in 2016, but has been a part of a research project at the University of Iceland since 2012. And we are obviously in the green ammonia space. I think that's obvious. But we are looking at the green production of ammonia for the future. Maybe to start out with very briefly, what is ammonia and why are we talking about that? Well, currently, so ammonia is NH3. And today, ammonia is the main ingredient in nitrogen fertilizers. And these are essential for food supply in the world, as adding nitrogen fertilizers can increase the yield from 50 even up to 100% of the crop. So that is obviously quite essential for the food security of the world, and especially with a growing population. Ammonia is currently produced through the Haber-Bosch process, and that process is using natural gas or coal as a feedstock, with then the accompanying CO2 emissions, and is now credited for approximately 2% of the global CO2 emissions because of that. These Haber-Bosch sites are very large. These are high capex. These are very big projects to make these factories, and they very much rely on economies of scale. And in most cases, they are also then linked to or close to a good feedstock of either gas or coal. So that is very often linked together. The process is using high heat and high pressure conditions within the process. So that also requires then a continuous operation, because shutting it down and ramping it up again is very expensive. So that it needs quite a steady operation. So this is what the ammonia looks like today. And as most of you are aware, there have been quite dramatic changes in the ammonia market in these past months. And that is a knock-on effect from the natural gas prices soaring up in the past months. But what is then the difference between green ammonia? So green ammonia is then produced from clean energy, not from gas and coal. That can either be done by making hydrogen with electrolysis from clean electricity, and then adding that onto the old Haber-Bosch. So you still have the Haber-Bosch plant, but you have a new downstream production of um, of hydrogen that can be made clean. There are still, though, quite a few technical issues with that, and specifically when it comes to the size, because the Haber-Bosch needs to be very big and running continuously to be economical. That means the then supply of hydrogen also needs to be in very high volumes and quite continuous. And this is doing that on renewable energy is a challenge, though technically possible right now. But the importance of green ammonia is, well, it's very important. It is highlighted in the Paris Agreement as one of these key chemical processes that need to be changed, need to be adapted. It is essential to keep a secure food supply in a zero carbon world. It's not really an option for the world today to just stop producing ammonia, because that also means we stop producing large amounts of foods in the world. But green ammonia and ammonia can not only be used in the fertilizer, it is also our carbon-free fuel. And that is, I think, where the biggest opportunity lies in the future. As ammonia can also be both used in combustion engines, so more traditional engines, but also in fuel cells. It's also an energy carrier, so it is actually easier to ship ammonia than hydrogen, and ship the same amount of hydrogen in the form of ammonia, because ammonia is quite dense compared to hydrogen. And energy storage, because that is an issue that is facing pretty much every grid in the world when relying more and more on sustainable energy. That is some very seasonal, so it can be very shifting within the day, but it can also be very shifting between seasons. So there is a need for quite a big array of energy storage solutions, and ammonia can be a very good fit for long-term storage. If you have a battery that depletes over time, if you leave it out, at the end of the period, you don't have any energy there anymore. But the ammonia can be stored for a very long time. So that is a great potential as well. But to realize this green ammonia future, we need both new technologies, but we also need adaptations to the sustainable electricity production. And that is one of the big challenges, technically speaking, is to fit the green ammonia production systems to the electricity production so that these are in sync. So what ammonia is doing is twofold. Well, we are focusing here on the ammonia production system, where we use renewable energy, nitrogen from the atmosphere, and water, H2O, to produce ammonia and oxygen as a side product. And that ammonia can then either be used directly into the fuel market, some of it directly into agriculture, or into further processing for fertilizers, for example, nitrates. What we are working on is the electrochemical process, where we use only electricity. So there's not heat nor pressure in terms of the energy that we are using. It's electricity. It's a zero emission process. There is no carbon involved in it anywhere. It's low capex. It can be in very small production modules. So our base production model we are looking at is a 40-foot container size, which would be producing around 100 to 150 tons of ammonia a year. So in the world of ammonia, that's a micro or even a nano scale of production. But for the user, that can be quite a big amount. And a key thing is the intermittent operation, that because we don't have heat or pressure, we can actually turn it on and off much more easily than if you always have to build up the high pressure and high temperature conditions. And this is what we're finding to be a key element when linking this directly to sustainable energy, like wind farms or solar farms, that you were able to be producing whenever there is electricity available and able to shut it off whenever there is energy shortage. And that also gives us quite a lot of flexibility in terms of where you have areas where there are regular energy shortages, that it's easy to cut these out of the grid. And the distributed production is, because it's very small and it only needs electricity and water, that can be something we can source in very, very many locations. So that gives it...
Olá, boa tarde. Ah, por causa do anidrido? É. Ok. Olha, não se importa de voltar agora daqui uma hora, porque agora estou numa conferência.
Christelle, can you
Não se
unmute?
importar.
Can you unmute
Eu vou
all
ficar
the...
aqui. Como chama já? É Diana, ok. Procura-me. Ok, até já.
So that is our vision, is to respond to these challenges by having a very flexible system that can operate very seamlessly with these renewable electricity sources, which is becoming one of the major problems with moving forwards with the green ammonia. Let's see here. Yeah, as I said, it's we have a core product, which is the electrocells. So these are cells in many kind of nuts and bolts of it, similar to a fuel cell, even though its internals are working differently. And then we have an enabling product, which is a 40-foot container. It's a housing for these systems. And we are focusing our first version into liquid fertilizer, so into the fertilizer market, and then our second version for anhydrous ammonia production for the fuel industry. The core of all of this is a special catalyst that ammonia has the patents for. And we are not dealing with any precious metals or rare earths. We are focused on metal nitrates, oxides, and sulfides. And the original idea came from looking at how ammonia is produced in nature, which is done with microbes. Microbes do this in the soil. And so the initial idea was that it's possible. It's done already in the natural world. So we're not defying laws of physics, but how do we synthesize this naturally occurring production at an efficient rate? And microbes obviously do this without heat and pressure. So how do we manage to synthesize that process to mimic what nature is doing? And that's where it began, the search. And it started with simulations. So DFT calculations and theoretical simulations of what kind of materials would be able to do this and work as a catalyst for this reaction. And that brings us then now to after all these years, to the ammonia and Fujitsu collaboration. But because we started all of this with calculations, EFD calculations and simulations for the initial catalyst formulation. Then we have taken these and brought them into the laboratory and started experimenting on various candidates from these calculations. We see things that, of course, a lot of results that we can then feed back into the simulations and to have an ongoing loop where we improve the calculation and simulations models with real world data that we are getting. And now in collaboration with Fujitsu, we are kind of stepping up that aspect of our work and adding in very exciting aspects with AI to help us read through all this data and spot things and help us to move this loop along so that we can optimize and steer our next moves in a better way and well, more calculated. Yeah, so that is, I think, everything for me, and I think we go to Fujitsu to explain more about and tell you more about the calculation and that side of things.
Okay, thank you.
Great. So, Crystal, I'll try to share my screen. And
I think it will work now.
okay, great, wonderful.
Great.
Can you guys see my screen? Okay.
Yeah.
Okay. And yeah, I'll go into the slideshow mode. Great. Again, thank you, Crystal, for the opportunity to talk to you. I'll turn on my video briefly, at least, so that you can all see me, hopefully. So again, I am Surya Josula. I work at Fujitsu Research in North America. I'm based actually in Sunnyvale, California. And what I want to do today is just give you a brief introduction to Fujitsu, the company, and then talk about why ammonia, why does Fujitsu care about the ammonia initiatives, and why we're trying to get into this market space, and also some of our technologies that Gjordborg alluded to when she spoke about the need for advanced technologies in green ammonia generation. So to get started, let me briefly introduce Fujitsu. You may not know, but Fujitsu is one of the largest information and communication technology companies in the world. We are the largest in Japan and the 5th largest worldwide. And we currently are headquartered in Japan, right outside of Tokyo, in Shiodome. We are about 132,000 employees worldwide. And we have a full technology and portfolio within our company. So the very motto for our company is to sort of, sorry, this seems advancing, to make the world more sustainable by building trust in society. And this comes down from our CEO down. So for us, sustainability, carbon neutrality, green energy, these are very critical to what we do as a company. And we are very closely following the UN SDG goals and seeing how our technologies can power some of the sustainability goals that the world is trying to achieve. So whatever we do within the company, in every product, service, research, we try to put sustainability and social responsibility at the top. And so that's how we sort of are, getting more engaged with the whole green energy and green initiatives. So like I said, our purpose is to make the world more sustainable by building trust in society through innovation. So in terms of innovation, like I said, I'm part of Fujitsu Research. We have about 1,200 researchers worldwide, and we work on research in various aspects of computer science and electrical engineering, material science, And our research centers are all over the world, Tokyo being one, the Bay Area, Sunnyvale. We have a team in London, in Madrid, in China. So we are sort of spread out. And we recently opened 2 new research centers, one in Israel and the other one in Bangalore in India. And so the teams sort of collaborate across the world, working on various technologies, but all towards sort of helping society through various aspects of innovation and building trust in society. So like I said, innovation is, we believe is key to solving our environmental, social, and economic problems. The key elements we believe are human centricity. So whatever we do, it needs to impact society and people, and all our technology research is towards that. We believe a lot in data. The future will be data-driven. Digital transformation is already taken place, and societies around the world are more and more connected. So how do we leverage human centricity, data that's there in society and the connectedness to sort of change the vision and improve, or how technologies can solve world's problems? So those are the 3 main areas where we focus on: human centricity, data-driven solutions, and the whole connected ecosystems. And this happens across the verticals, whether it's energy, resource management, manufacturing, smart cities, customer experiences. We leverage our strengths in these 3 main areas to sort of solve problems. So every year, Fujitsu releases what we call our technology and services vision. And in this document, we sort of highlight where we see the future headed over the next several years. With the recent pandemic and the experiences, what we are seeing is, the physical and digital experiences. There's no real border in the world. I mean, we have the sort of the borders between countries, but essentially we have one world. And how do we sort of empower societies in a borderless world in the future, as we all are coming together? Then there's a whole nature of how things are sort of very unpredictable. So, with the pandemic happening and with the future, building resilience in societies is very critical. So how can technologies enable that? Then there is trust. So, privacy, trust, security are very critical, not only for human data that we create, but also to enable a supply chain, enabling people to connect safely and securely. So trust is actually very critical, we believe. And finally, innovation and discovery. So how do we, discover new materials, new ways of doing business, and how do we sort of further our technology vision with that? So to do this, we have what we call at Fujitsu 7 key focus areas and 5 key technologies. And let me talk about sort of the technologies first, because I'm from a research organization. So in computing, we have invested a lot in high performance computing. Currently the world's 2nd fastest supercomputer is a Fujitsu computer. It's called the Fugaku. And we're using the Fugaku to solve all sorts of social problems. During the pandemic, we used it for simulations of molecules, for example. We're looking at weather patterns. We are currently also working on complex CFD simulations using Fugaku. Fujitsu also has invested heavily in quantum computing. So we have what we call the digital annealer, which is a quantum-inspired system. And the digital annealer is used for solving complex combinatorial optimization problems. We are currently working with many companies to address their optimization problems, whether it is traffic routing, or whether it's new drug discovery. So the DA is very well suited for solving those kinds of problems. We have also announced a new quantum initiative. We are working on the next generation quantum computers. And in the interim, we have released what we call a quantum simulator. The quantum simulator enables you to work on qubits and use the simulator to solve current algorithms or whatever quantum tests that you may want to do. So that is sort of our story on computing. In networking, we are very focused on 5G and also on 6G. So radio access networks, we are very strong in photonics. also optimizing network traffic through artificial intelligence. So we have a strong networking business that's actually based in Dallas in Texas. Then artificial intelligence, we are focusing on explainable artificial intelligence. So, opening the black box of AI to see what's actually going within the AI system. And then ethics is very critical for us. We have a very strong collaborations, for example, with the University of Oxford. And we have a team in London that's focusing on ethical AI and what that actually means for companies. And then, of course, we have Discovery AI, which is more graph artificial intelligence, and I'll briefly speak about that later. And then we have a program on automatic machine learning. So bringing the power of machine learning down to the business user, as opposed to having somebody to train the models, we can actually do machine learning, the training of the models automatically. So that's an auto ML project that we have. And then finally, in data and security, we were always very strong in multimodal biometrics. So Fujitsu had the palm vein authentication system for the last 10 years or so. It's one of the leading biometric authentication systems in the world. And now we have combined it with facial recognition and other kinds of biometrics as well, like fingerprint. We also have invested heavily into blockchain technology. So we are active members of the Linux Foundation Hyperledger project. And we have worked on essentially blockchain interoperability and how can you bring multiple blockchains together. And again, and cybersecurity is another main area of focus for us. The last area is what we call connected technologies, converging technologies rather, sorry. Here we are looking at how do we bring the power of all the other technologies together? So for example, human behavior modification analysis, facial expression recognition, digital twin technologies. These are all what we call converging technologies. And so these are the main technical focus areas for Fujitsu research. And they would be powering what we call Fujitsu U-Bands, which is our 7 key focus areas, all the way from sustainable manufacturing to healthy living, business applications. So we are a very technology centric and technology focused company, and then we help our customers solve their sort of business problems in several key vertical areas. So why ammonia? So Fujitsu at core is an IT company, but why are we very interested in ammonia? And so one of the things that we believe, like I said, is sustainability is very critical for our corporation, and how we believe that that's the way of the future. And we think one of the areas is green energy. So how do we generate energy which is environmentally friendly? And when solar, wind, and other forms of green energy are not available, how do we sort of power our data centers and our customers' data centers and the entire businesses, right, with green and sustainable energy? So as you can imagine, almost 100% of our business relies on power. And so we are large power consumers within our company. And we across the board, whether it's hardware, software, we operate clouds, data centers all over the world. And so Fujitsu as a corporation is very interested in completely making our own internal operations green, and then using that knowledge to actually power our customers' conservation and green energy initiatives. And we believe that ammonia could dramatically change how the world's energy supplies. And when we do not have other forms of renewables, ammonia could be the solution that the world is actually looking for. And so how do we support this whole the hydrogen economy and the power generation economy? And so the goal of Fujitsu research that I'm part of is to collaborate with innovative companies like Ammonia and bring our technologies to help solve the ammonia production processes and helping it improving it dramatically and bringing the power of our technologies to the ammonia production challenges. So now what we see, as Kjordborg referred to, so the drawbacks of the current system are that the Haber-Bosch process has been around since the early 1900s. So it hasn't, I mean, there've been some improvements, but we believe that there can be significant enhancements to make it, much more green and make it sort of, towards green ammonia. And ammonia is very energy intensive and it produces a lot of greenhouse gases. So if we can come up with a more efficient way of generating ammonia, And then that would solve, like I said, not only the energy problems, but the whole ammonia is used in so many different ways. And so that's where we believe we can add value with our technologies. The other thing I want to mention is that Japan has a major emphasis on hydrogen and ammonia. And as a Japanese company, this is a very interesting area for us because Japan has some unique challenges, as you can imagine. It's a sort of a small country, very mountainous, and the urban areas are very dense. And also with the recent problems with the nuclear energy, with Fukushima Daiichi and the problems that we had there, we are looking at alternate ways of clean energy, for example. And the Japanese government has announced a major roadmap for ammonia as a fuel. And they are investing heavily in the supply chain because some of the hydrogen, the ammonia supply chain already exists. So how can we leverage that, right? So to sort of supply green ammonia to the various areas that need it. And Japan is sort of leading the world in the whole hydrogen and ammonia economy. They've published a roadmap for the next 30 years in terms of how they see ammonia sort of solving the road to green ammonia and sustainability. And many Japanese companies, in addition to Fujitsu, have announced ammonia-related initiatives. So across the board, Japan has a major focus on ammonia. And so it fits very naturally into Fujitsu, being a Japanese company and also a very technology-focused company, to be part of the ammonia ecosystem. And if you look at our technologies, I briefly introduced our technologies earlier on, but wherever you see in the ammonia life cycle, it's production, transformation, transport, and use, everywhere there is a need for technologies. So for example, in artificial intelligence, Gyurborg briefly referred to data. So one thing that we are discovering is that we have a technology called Deep Tensor, which is an artificial intelligence technology that analyzes graph. So we can look at graph data, nodes and edges, and do analytics on that data. And a lot of the data that is generated as you're looking for new catalysts, for example, is a sort of molecular level data, which is it has a very graph-like structure. And so, we believe that Deep Tensor, the technology that we have, can be used to solve to identify new molecules, for example, right, by analyzing the graph structure. We also have a material sciences research focus. So as you are trying to identify new materials, you will need adsorbent development, thin films, membranes. So all that stuff, we have a lot of focus on material sciences, and we believe that is also key to the green ammonia. Then finally, we come to supercomputing. I briefly mentioned Fugaku, whether it's Fugaku or our other HPC clusters. The problems that you need to solve, whether it's computational fluid dynamics problem, density functional theory, all these require high performance computing. And so what I'm trying to say is across the board, as you're looking at the ammonia ecosystem, technologies can play a critical role in solving specific problems. And we believe that the technologies that we have, whether it's AI or high performance computing, material sciences, can be applied to some of these problem areas. So finally, I just want to end with the partnership with Ammonia. So we are very happy to be collaborating with Ammonia. We believe in their moonshot idea of generating ammonia at room temperatures. And we found a very good synergy between our technologies that I just mentioned and what Ammonia is trying to do, and the kind of data that they're generating and the kind of simulations that they're doing. So there's a very good fit with our research and our focus areas and Ammonia's. And so we're currently collaborating with them on solving some of their technical challenges using the Fujitsu technologies. So that is essentially a summary of Fujitsu, our technologies, and how we believe we can sort of bring them to bear to solve some of the ammonia challenges. So that's the end of my presentation. Stop sharing.
Thank you so much. Thank you very much for your both presentations. Very interesting. Do the participants have some questions? Nobody has any, no question? Ah, yes. Ah, Christoph Held. But you, yes, I let you.
Hi. Yeah, thanks a lot for this amazing insight into this business. I think is no, we need not to discuss how important that is, and this is really a success story, I guess. Di- this idea of having 100, what was the capacity? 150 annual tons. So any ideas to increase the capacity? And you told us that I'm not sure if I put it right, per ton of produced ammonia, you need 12 megawatt hours of energy. Any thoughts on, or can you give us a hint how this compares to the actual classical route?
Yes. Yeah, so to the classical route where you are using gas or coal, this is in joules, slightly more energy, but this is 100% electricity. And also we are competing with a process that was invented in 1910 and has been optimized for 110 years. So our product, first product in the market might not beat them in the gigajoules when you're taking that aspect. So far, I mean, there are theoreticals that using a electrolyzer and then Haber-Bosch kind of still, so retrofitting a Haber-Bosch to work with electrolyzers to make hydrogen, that they could reach these similar numbers, but that still has not materialized that I know of at least. So in gigajoules, yes, this is slightly more, but still, if you're looking at the global average, this is actually similar, but we are benchmarking ourselves against European factories.
And
yeah, so that is kind of what we're looking at. And when it comes to the capacity, we are focusing, I mean, of course, in the future, we might make bigger electrical cells. That is the core unit or the smallest unit that we are working with. But they are also quite easily interconnected or stacked. So we can make a bigger factory by adding more containers. One of the reasons that we like this particular size is that in terms of energy consumption or energy needs, at full capacity, it is actually working quite well with a full-size wind turbine on land. So we are looking, for example, at projects where we have one of these containers next to a windmill. So they fit one-on-one. And one of the benefits is with that is we can circumvent both the laws and the cost of moving the electricity over a grid. Because there is quite a lot of both cost, but also just laws related to moving the electricity around. So the less we can move the electrons around, the more we can get out of that renewable installation.
okay, thank you. What, if I may add, what are you actually researching on? So is your research now, so with the money that comes in now, so is your research focusing, let's say, rather development of new catalysts, or where are you putting now the effort?
Oh, it's in optimizing the catalyst. So that the catalyst we are, so we're focusing on the in the laboratory. That's where we are stationed right now, is in the laboratory to get the catalyst composition, and it's a lot of material sciences right for scaling, so that we can make big electrodes that still work at larger scale, not just in our lab. So that is really the focus, is to get the catalyst composition. Yeah, exactly right. And it's where we're also using them now. And one of the aspects of this project with Fiachu is to help us in that, to speed up that work.
Great. Thanks.
Yeah, thanks.
Thank you. We have a question from Christian Barca. Christian, may I let you ask your question?
Oh, hi everybody, Christian Barca from Ex-Marcia University. Yeah, I have just a question, a general question on the general topic. So I was curious to know if you have some idea about, for example, LCA analysis, mainly pair, so the green process of recovery, production of ammonia from air, nitrogen to the classical processes of ammonia recovering from waste, for example, air stripping, ammonia stripping from effluents from anaerobic digestion. Just a general question. So.
Yes. I think the main issue often with that comes with recovery from waste is the process to get that into a usable form, and especially to get that into anhydrous ammonia for fuel use. I've not seen that being done anywhere, but it is a fun thing to mention that we have, as this is focused on ammonia, we actually have a side product that we are looking at that takes in ammonia, and one of the aspects that we're looking at is exactly to accompanying this with ammonia that is recovered from waste. And I think because a lot of the waste treatment is already treating ammonia, but just so that it isn't harmful, but not in a useful way. So they're not making anything useful out of, they're more neutralizing it. And I think there's a lot of potential in that to actually utilize this ammonia properly, and then at the same time get a much better LCA. So I mean, minimize the environmental impact, but we don't have enough waste in the world. It could be, I think, focused on fertilizers, and I think there's definitely a lot of opportunities to utilize much more of that ammonia that is now just wasted. And I think there are quite opportunities, and we are looking into here with the here in Iceland. We have been in a collaboration project with a research institute here, looking into exactly these kind of issues, what kind of waste streams can be used, and what kind of technology would that require. But if we want to go into switching out fuel for the world, specifically shipping fuel and aviation, for example, there's a lot of discussion on moving that to ammonia. Waste ammonia is never going to be sufficient.
Okay, thank you.
One more question? Yes, Pavel?
Hello, Christelle, thank you for arranging this, and Gudberg and Soraya, thank you for actually participating in this presentation. I would like to ask you first about what are the biggest challenges what the ammonia currently faces? Catalyst development or grid or valorization?
Catalyst development in research terms, or so in the science part and development part, it's
so what do you use right now?
So we are now, so we don't have a product on the market.
Okay.
We are in development stage. We are focusing very much on the nitrates, so metal nitrates.
But metal nitrates or just nitrates?
Metal nitrates.
Metal nitrates, but nitrates give you already a big background or some kind of.
Exactly, and that is what has been also quite a big part of the development in the lab, is to have an experimental setup that we can rely on and find the quantitation methods to work with properly. We have I'm actually very proud to say that we have an excellent team there and have, have really developed a foolproof system so that we can trust our results, because this is a huge issue in this space in general, in the science world, is that there is a lot of positive results that cannot be replicated, and so false positives. And that is kind of the biggest issue we see in this space, scientifically speaking, is the amount of false positives.
Did you have any experience of false positives?
Oh, we've seen it, but then we double check and triple check, and we have we never go and say yay before we actually go through all the steps and all the hoops to make sure that this was an actual and reliable result. But we are working with completely closed system, for example, which is essential.
Yeah, it is, because even if you breathe air or let the air,
ammonia is everywhere, because you were always working with such small quantities in these experiments. It has to be a completely closed system. You have to be extremely thorough in cleaning.
So which metal works best for you at the moment, for the combination of metals?
I want to say that we are working now mostly on niobium and zirconium.
Oh, niobium and zirconium. Okay. Thank you.
And we have actually some published papers. Some of these, we're not letting anyone know the exact stuff we're working on.
Oh, okay.
We're in.
So in the sense,
in that area, in that region.
But you don't also specify what type of a catalyst you have, or you do have, if you have the IP for that, or it's a trade secret at this stage?
It's a trade secret. So our patents include a group of materials. Then our actual catalysts are a mixture or more precise catalysts, or more precise structures than the patent actually.
Okay. Yeah, because it needs to. Are there raw materials? I mean, zirconium is probably not, but.
Rare earths, you mean, or like?
Yeah, I mean critical.
No. So we actually, it's one of the things that the founders did when they were founding the company. One of the first things they did was to map the world reserve of all of these metals and all of the metals that are specified in the patent, for example.
Okay.
And there is one, I think I am telling the right one. I think it's ruthenium, something that is specified in the patent, because theoretically it could work, but we've never done any.
It could.
And we're not planning to use that ever.
Yeah, but it's a little bit like that.
I mean,
as well as
in there, but it's very expensive and it's a rare earth material. I mean, we do not want to be using being relying on that.
Okay, that's great. So I wanted to know more about like how you participate together with Fujitsu or on your own with, for instance, European innovation. How do you go for initiatives or the new things like the Pathfinder or FET as they were known before? Oh, you do.
We are so the project with Fujitsu is just not linked to any grant scheme or anything like that. It's just a joint project with the two companies. However, we just now received that we were awarded a grant from the Horizon with collaborators in Europe, so across Europe. And we have in the past had a lot of projects working a lot with universities. I mean, we are a university spin-off. That's where our roots are. So we very much like to work with in collaboration with academia and research projects.
And then probably it's the right time to switch to the Fujitsu if Saruya is still here with us.
Yeah, I'm here. Please go ahead.
So could you tell us a little bit more, because your presentation was really good and at the selling point, but you didn't really go into the details of how you work together and what type of the projects you work together and how you help each other to design the new materials or the new systems?
Oh, sure, sure. So basically, we have 4 research staff members who are actively working with the Ammonia team in Iceland. The researchers are based in Japan, and currently they're focusing on 2 areas, bringing in HPC and in AI. HPC, we are actually helping Ammonia with simulations. So how do you
simulations
sort of
of what? I apologize. Simulations of what?
Of discovering new catalyst materials, right? So
Okay.
how can you enable that? So that is the focus of the high performance computing team is simulating, especially on Fugaku and some of the higher end systems that we have. We also have an AI team that's looking at graph data. So Ammonia has generated a lot of graph data in their bench process. And we are looking at that graph data and using our graph analysis technology to see, are there any common themes that are emerging, right? Is there any insights that we can get from that graph data to look for example, new molecules, or are there any patterns in that graph data? So they have a lot of that, and they've sent that to us, and we are currently analyzing that using our graph analysis technology, which is more on the AI side. So that is essentially the investment that Fujitsu has made. It's a research level sort of collaboration on these 2 main topic areas.
I believe both of you have competitors. Could you name a couple of them or a couple of approaches? And this is the last question. Thank you.
And I mean, Fujitsu has hundreds of competitors, just given the size of our company. Yeah, so I mean, so we compete. If you're speaking specific about computing and AI, of course, we compete with
In materials.
Material science. Yeah, I mean, we compete with IBM and HP and Amazon to a certain degree, right? With our cloud centers. And then AI, we have a lot of competitors. Yeah, so I will let maybe Göteborg answer. Fujitsu just has so many competitors. Göteborg, you want to talk about that one?
Yes. So we have kind of twofold competitors. It's the traditional ammonia.
Yeah.
And that's kind of obvious. And then there are some other companies or research groups. There are not that many companies yet that are looking at somewhat similar methods to what we have. Not necessarily the same, but so really new production methods for ammonia. There, when it comes to these aqueous and the system that we are looking at, we are at that forefront of that technology currently. But there are also some other interesting avenues, and I think
that's great. That's great.
Yes, it is, and there's been like an explosion in the research in this field.
It was, yeah, for sure.
I mean,
so
I started 2018, and just the change in these 4 now is amazing. But unfortunately, a lot of these are false positives. Still, so there is now kind of a push, and I hope we are trying to do our part in that to, at least to some degree, standardize the methods. So how do we quantify this? How do we do these experiments so that we can rely on and use data from each other? As that we work a lot with the university, so we try our best to publish what we can. So the methods we're using, we try to publish scientific papers whenever that can be done, when there are not too much secrets, but that's how we can solve this. And so we also follow very closely a few groups around the world.
That's wonderful. I just wanted to ask one more thing, because I've been asked this once before, and we were actually quarreling about this. How do you project the ammonia market, especially the green ammonia market, to be growing within the next, well, let's say a decade or 2? And this is really, no, it's a bet growing. So if it's going to be linear, or it's going to go like upwards, based on exponential, you think?
Yes, and I'm taking that from both how this exploded already, from what it was, and the amounts of projects that are being. And I think now with the crisis in Ukraine and the war, I think we're even seeing a faster push, not only environmental, but also seeing a push for more, not sustainability, but self-sustainability.
Yeah.
That's want to be self-sufficient. But different areas of the world that currently are not self-sufficient for energy, for fertilizers, and they're the FAO, the Food and Agriculture Organization of the United Nations, is estimating, I think it was tens of millions that will be hungry, and there will be a crisis because of fertilizer supply shortages because of the war.
But then we have another question, because if we're talking, I heard about the company being set up and things being set up actually in Mauritius. So where it's warm, you have a lot of sunshine, and so the electricity is going to be generated by solar power and then fit up into the ammonia. But what about the cold countries, like some of us? I come from Estonia, that's why I'm asking this.
Yeah, I'm from Iceland, so I probably win that contest. Of course, that's going to depend country from country. I mean, here we're not going to be using solar panels. We don't have sun in the winter, but we can have wind. We have
wind is good. Yeah,
hydro, and that's also because we're going to have so many different, and we need energy storage exactly for that. Because even here in Iceland, there are some that use solar panels, but then you just need energy storage, a lot of it.
Yeah.
And with the prices of these solutions going down, you are actually starting to get feasibility for example, solar panel further and further north. But then the energy storage becomes an issue, and a bigger issue. I mean, now if we're running 24/7 coal electricity production, it's not really an issue. But if we're relying completely on wind, it's a very different story. So that's also the flexibility. That's going to be very important.
Thank you so much.
Yeah, you're welcome. Yeah, I can see there's one.
Christelle, we cannot hear you.
Sorry. So we have a question from Elvira Casas. She has a question about durability or regeneration. Have you already approached these issues, or are they considered in the future research steps?
No, we have already considered that. And we foresee that our catalyst or the electrical cells will need to be regenerated or like refurbished. And we are actually now this spring, we became a partner in a grant proposal. I don't think there are results out of that yet, about recycling and refurbishing of catalysts, because that is something that we envision doing. So it's one of the benefits of being a completely new company, that we can actually think about the entire life cycle of the products from the beginning. We're not dealing with some legacy stuff. So that's what we envision, is that they need to be refurbished regularly. And we have already thought that we would be a part of that. It's not something you throw out. It's something that we bring back and have a factory that specializes in that from day one.
Thank you. No more questions? No? Okay, so if there are no more questions, I propose to finish the meeting. Thank you again to the two speakers. It was very, very interesting, and thank you to the participants for their interaction. I think that this meeting was very fruitful. I wish you a good evening and a good day to Mr. Joshua, because it is very early for you.
No, that's not too bad. Thank you very much. Thank you.
Thank you very much.
Bye.
Bye.
Thank you, all of you. Thank you.